All right. Welcome to this session. So this session we have 6 interesting papers. Our first paper is SPLENDID supporting parallel LLVM-IR enhanced neural decompilation for interactive development. And our speaker is Susan Tan from Princeton University.
Hi, everyone. My name is Susan. I'm from Princeton University. Today, I will present SPLENDID, supporting parallel LLVM-IR enhanced natural decompilation for interactive development. This is joint work with Liberty Research Group from Princeton, Argonne Lab from Northwestern, and Argonne National Lab. So as programmers, we all know that writing a parallel program is notoriously difficult and error-prone. One way to resolve this issue is through automatic parallelization by the compiler. However, the programmer can still help with parallelization. Consider the following situation where there's a printf statement inside of a sequential code loop. And because it's sequential code semantic, this printf can only be printed in order. But the programmer may be able to tell the compiler that out-of-order diagnostic printing is actually acceptable. And compiler, by knowing this fact, can say, okay, now I can parallelize the loop better. Thus, because the compiler cannot expand the set of valid outputs of a program, parallelization will always benefit from the programmer and the compiler working together. We call this collaborative parallelization. And collaborative parallelization is not a new concept, and it has been done in the past. Let's look at an example of how it was done in COMSET, which is implicit parallel programming. And in COMSET, the compiler will analyze the program and report dependence back to the programmer. And the programmer, by knowing where the dependencies are, will do manual parallelization through adding annotations. And in this scheme, the compiler only suggests where the parallelism can be found, but the compiler will not parallelize the program for the programmer. So the programmer, it's still upon the programmer to do the parallelization. So this brought us to the question, is there a better approach to collaborative parallelization? And for this question, we did a study on all the loops within 16 polybench benchmarks. And we took the manual parallelization from Cavazos lab. They use OpenMP to parallelize these benchmarks. And for automatic parallelization, we use Poly. And we found out that there is a large overlap between what a compiler can parallelize and what a programmer can parallelize. So we started to imagine that a better approach to collaborative parallelization will actually freeze the programmer from doing such redundant work. Moreover, we imagine that collaborative parallelization should obtain the union of the parallelism without dismissing either the work of a compiler or of a programmer. Lastly, we want to present the full work of compiler to the programmer so that it can help the programmer to narrow the scope of optimization. So with this in mind, we want to introduce SPLENDID. And SPLENDID's approach to collaborative parallelization is, before any manual parallelization, we will let the work of an automatic parallelizer directly be presented to the programmer at the source level. So let's look at an example of how that can happen. Suppose there is a sequential code and an automatic parallelizer will try to parallelize the loop, and SPLENDID will then translate the work of the automatic parallelizer into source code using OpenMP and C. And with SPLENDID generated code, the programmer already has a better starting point, which is the code already parallelized to begin with. And on top of that, with SPLENDID generated code, the programmer can easily spot that automatic parallelizer can only parallelize the loop when A and B do not alias. So with that in mind, the programmer can then focus its optimization on the case when A and B must alias. So with that, SPLENDID is able to reduce manual effort, but increase the level of parallelism. So in order to know what SPLENDID is, we want to look at first where are all the automatic parallelization frameworks are at, because that will define what SPLENDID does. So we looked at all the state-of-the-art automatic parallelization frameworks, and all of them are at the LLVM-IR level, which means that now we can finally define what SPLENDID is. It is a decompiler that generates natural, portable C and OpenMP code from parallel LLVM-IR for the purpose of collaborative parallelization. And with SPLENDID, the programmer and the compiler can finally fall in love with each other because they can communicate. So the question is, if in the essence Splendid is just a decompiler, then why not using an existing one? To answer that question, we started looking at an existing decompiler. So before I say anything else, please do not try to interpret this code because it's just too hard to understand. So this is an example of a polyparallelized code decompiled with Relic, which is an LLVM-IR to C decompiler. And essentially, we can see that there are a lot of parallel runtime library calls translated as it is at the source level, because IR level parallelism is just expressed as runtime library calls. And then we can see that all the loops are translated into do-while fashion. This is because a lot of automatic parallelizers, they will actually canonicalize the loops to be in rotated form. And without knowing that, a lot of decompilers will just decompile the loops as it is. And lastly, if you look at the green boxes, we can see that all the variable names actually don't tell us anything about the code semantic because they actually correspond to the virtual registers. So we see that the code from previous generations of decompilers, the decompiled code lack portability and lack naturalness. This will increase the difficulty of human interaction. We're not trying to say that previous decompilers are bad. They're actually made excellent for their own purpose, such as reverse engineering or security or software validation. But it's for our specific purpose of collaborative parallelization. We really want the code to be portable and natural in order for a programmer to easily interact with. So now let's see an example of how Splendid will translate such parallel LLVM-IR to portable and natural C and OpenMP code. The first thing Splendid does is translating parallel runtime library calls into OpenMP pragmas. And because of that, Splendid decompiled code can be compiled with any OpenMP runtime libraries. And note that Splendid would also choose the most performing set of pragmas when multiples are applicable. And next, Splendid will actually detransform loop canonicalization so that the loops will be translated back to for loops, even if the loops are in rotated form at the IR level. And this will make pragma selections much easier because OpenMP imposes strict rules on loop structures. And note that Splendid actually does not detransform any other performance-enabling transformations, such as loop unrolling or loop distribution. And as you can see, that Splendid will present them as it is at the source level without sacrificing any naturalness. Lastly, Splendid will restore source variable names through relating virtual registers to source variables through debugging information. The major challenge here is that at the middle end, there are a lot of aggressive optimizations that happen that makes virtual registers have overlapping lifetime. And when they're overlapping lifetime, they cannot be mapped back to the same source variable anymore. And Splendid is able to detect and eliminate any naming conflicts. And please go read the paper into the details. So lastly, let's look at some of the key results. Before that, let's briefly talk about experiment setup. Splendid is evaluated using 16 benchmarks from Polybench benchmark suite, and the performance results are obtained on a commodity shared memory hardware with 28 cores. The most important result we want to show is Splendid's ability to enable collaborative parallelization that practically reduces manual effort while increased parallelism. So let's use Gember as an example. Compared to either manual parallelization or compiler parallelization, Splendid's collaborative approach, which is decompile what Poly does into source code. And on top of that, we only added one line of code and we are able to double the performance. We did not do that just for Gember, but for 7 embarrassingly parallel programs where either manual or compiler parallelization should have been sufficient. And there are still cases when compiler alone can already parallelize a loop pretty well. And for these situations, Splendid is able to lift up the IR level parallelism back to source level. So using 2mm as an example, Poly actually does a great job parallelizing 2mm, but with Splendid, it's able to translate IR level parallelism back to source level. So the programmer can then use the compiler of its own choice. For example, in this case, we're able to compile it using Clang and GCC, and you're able to obtain the same speed up. And we did that for 16 benchmarks and obtained 11 times speed up for that was originally only available in Poly, but now we're able to make it universally available at the source level. And one of the benefit of source level parallelism is then it gives the programmer the flexibility in choosing between compilers that would have the optimal performance. So in the case of MVT, using GCC will actually double the performance compared to using Clang, probably because GCC has a better backend optimization for MVT. So in conclusion, a decompiler that produces natural parallel code can enable more efficient collaborative parallelization between the compiler and the programmer. This paper thus presents Splendid, an OpenMP and C decompiler that produces portable and natural code. And although Splendid was made for collaborative parallelization, we do believe that the natural code that Splendid provides will help us in the future with code migration and debugging and performance engineering. And with that, we're hoping that we can get some collaboration with you guys. And thank you. Now I'm able to take some questions.